I'm going to talk something very different from the Martin's and my previous talk. I'm going to talk about the neural and the non-neural correlates of those time-varying resonance states functional connectivity. And here's a very short introduction. When we say that functional connectivity, we actually mean the temporal correlation between the fMRI signals. Typically calculated over the entire session with assuming the relationship is stable. And however, the brain is such a dynamic system, so the different regions may interact with each other dynamically. For example, if we have a correlation like between three brain regions, A, B, and C, it could actually result from the interaction between A and B during some time periods, plus the interaction between A and C during some other time periods. And I think the stationary correlation actually ignore all of those information. And that's why the early study trying to explore those dynamic resonance state connectivity. And the most straightforward methods just use the sliding window methods. Basically, you just compute the correlation within a very short window, and then see how it varies across time. And the early study did found, for example, the correlation between the default mode network and the taskbar region actually can go from the very positive to very negative. And also another study found that if we incorporate those information into our classifier, we can actually improve the accuracy. And it seems very promising. And I think that's the reason why right after that, a set of the methods has been proposed, try to understand and also quantify those dynamic resonance states fMRI. And here it's just some example, but I won't go to the details. And because today my talk will focus on more like the three questions. First one, what causes those temporal variation in the resonance state fMRI correlation? Are they neuronal or non-neuronal? Do they truly reflect a non-stationary relationship or just due to the sampling variability? And first, I just want to say maybe the pairwise correlation is not the best way to quantify those covariance structure in the fMRI because it tells us very little about those high-order correlation, which I defined as like the covariance of a lot of brain regions. For example, these two cases, you got identical pairwise correlation, but their high-order correlation could be very different. This is especially critical for the fMRI because we know fMRI data has much more spatial voxels than the time points. So if you calculate, like for example, voxel-based analysis, you calculate all possible correlation, you will get more correlation than your actual data points. So that's a redundant representation. And also, based on those network patterns from the correlation analysis, it must be very strong high-order correlation in the fMRI data. And here just like an example of just an EPI imaging. We just play it as a movie. If you just watch this movie carefully, you can see there are patterns coming and going. And you can just see if you have a time series from for example, the post-cingulate cortex, you can correlate with all of the other brain voxels. You got a nice map and showing the default network. And you can, alternatively, you can just use a color to encode the deviation from the temporal mean. Then if you use the subgroup of the time points showing the highest signal in PCC, you basically got a very similar pattern. But that's not strange. That's a definition of the correlation. But what surprises really, you just pick up one point. Actually, you already see those very clear patterns. As clear as those correlation maps, you already see those patterns. And if you just take a look at the different time points, you actually see different types of the patterns. And I want to emphasize, for example, the last two, they actually show, those two patterns show significant overlap, but they are definitely different from each other. Based on this observation, we have proposed to try to classify those time points based on their spatial similarity. Then we average those time points within the subgroups to derive something called the core activation patterns. And we also believe those dynamic connectivity is actually largely determined by those instantaneous co-activation. For example, just one example in the motor network, if you have like the time point number 3 has like those sensory region co-activation. So if you put like the short window there, then you will see strong correlation within that network. But if you move the window away, then you don't see much correlation within the sensory network anymore. So what we can learn from those CAP results, first, I think instead of the dynamic connectivity, we probably should, I think it's actually coming from those dynamic brain co-activation patterns. So instead of that, to understand those dynamic connectivity, we need to understand those co-activation. And the second one is whether it's neuronal or non-neuronal, just based on the pattern, you can say. They definitely see very clear network pattern. Some of them even show some dynamic nucleus. So based on this observation, we tend to believe it's more like the neuronal. And how this question is tough because stationary or non-stationary, because the dynamics doesn't mean the stationary. For example, for the spatial ICA, you can get the time course for every the independent component, but it doesn't mean it's stationary. ICA actually assumes those voxels belonging to the same network. They have a fixed relationship. How about the CAPs? Based on this one, CAP could be just like the peak activity of those different networks. But we actually argue that's not the case. When we use the CAP methods to decompose, for example, the default mode network, we found multiple DMM CAPs, which has a significant overlap, but very specific feature. For example, those co-activation in those very different subcortical structure. And also, I think people also use the temporal ICA. They also got similar results indicating one brain region actually can dynamically involved in different brain configuration. Based on that, I think I prefer those dynamics is probably non-stationary. But I think so far we just try to understand those questions based on the fMRI signal itself. And recently there is another study using the optical imaging. They simultaneously acquire the Kelsey imaging and the hemodynamic signals from the mice. And they indeed found those CAP patterns in the Kelsey imaging. That's a neuronal. And they also demonstrate those dynamic functional connectivity of the hemodynamic signal within those short time windows, actually largely determined by those CAPs. And this study also used a simulation to confirm those dynamic connectivity is indeed non-stationary, because if you use the simulated data, which has identical like covariance structure and also the spatial pattern, but those, if you calculate the kurtosis, actually those simulated data doesn't has as strong value as those real data. And so far we talk about the CAPs, which is more corresponding to the network-specific correlation. But how about global signal, which is another dynamic component people found for the resonance state fMRI, and a lot of people already show this global signal is sensitive to the brain states. During the light sleep stage, it's very, very strong, and for the compared with the eyes open condition, the sleep conducive eyes closed condition also show larger global signal. And if you use a caffeine, you can effectively reduce this component. But if you use the hypnotic drugs, you actually got the opposite effect. And we have been trying to understand this global signal from the perspective of the brain co-activation. So when we apply this CAP decomposition on the data sets with or without using global signal regression to remove this global signal, we found the interesting results. This global signal regression has dramatically different effects on different types of the CAPs. It's for the sensory CAPs, the effect is very strong. It just indicates, if we regard the global signal as a global co-activation, this global co-activation actually occurs preferentially with those sensory regions. And so this makes us hypothesize those global signal actually induced by certain temporal events. So we go to the epoch signal we also check the global signal. Here is more like the mean spectrogram over all of the channels. And during the steep condition, we do see a very characteristic event showing the signal power change in 3 distinct frequency bands. First is the middle frequency reduction, then followed by gamma frequency increase, and then the low frequency. We call this one as a sequential spectral transition, and we also, it just occurs repeatedly. We also check those SST under different brain conditions. It's just to show very similar state dependency as those global signal. Yeah, it's strongest during the light steep and weaker during the eyes closed condition and almost gone during the eyes open condition. Therefore, we suspect maybe these SST events actually induce the global co-activation, and that's a global component. To test that, we just use a simultaneous fMRI local field potential from the monkeys. And you can see from this figure, we almost found a one-to-one correspondence between those SST and the global signal peaks. And alternatively, if you just do the average of those segments of the spectrogram based on those global peaks, you see those SST patterns. We further confirmed their correspondence in 2 different ways. First, we checked their spatial pattern. The gamma band power increase in the SST actually show a sensory dominant pattern. If we do the same thing for the fMRI data, just get the global co-activation pattern of those time points showing a big global signal, we actually show very similar spatial pattern. Also, based on the SST, we see a middle to low frequency spectral transition, which just indicates like the arousal drop. And if we take a close look at this global caps, we actually found those subcortical wake promoting region. Actually, even though almost everywhere the signal goes up, this specific region actually shows a deactivation. And then, so far, I only talk about the neural contribution to those resonance state fMRI dynamics, but how about the non-neural contribution? The first one I think people found is the physio signal. For example, if you have a deep breath, you will have a profound effect on fMRI. People then found the correlation between the respiration value and the resonance state fMRI. That's the same thing for the cardiac rates. And later, people found that the head motion also can increase the local but decrease the long-range resonance state connectivity. That's both true for the intro and the inter-subject analysis. For the intro-subject analysis, if you just temporarily scooping out those high motion time points, you actually can reduce those local connectivity and recover those long-range connectivity. But so far, I think most of people interpreted those results as a causal. For you, if you have the non-neural noise, then you induce a change in the resonance state connectivity. But what we really have is just a correlation. Now we know that actually the arousal can induce profound change in the resonance state fMRI, including the connectivity. And the people also documented those arousal can change, for example, the physio data, the motion, head motion as well. So we're wondering why the correlation between those non-neuronal noise and the resonance state connectivity is actually spurious, caused by the arousal. And that for the motion and the resonance fMRI correlation, I think the reason why we suspect that is a common motion matrix device is actually sensitive to the large fMRI signal change in general, including those global signal. And so for this study, we just, in addition to those motion matrix, we also define 2 additional matrices to quantify the arousal level. One is the global signal amplitude, another one is the DI. If we do the temporal scooping based on these 4 different matrices, actually we see very similar trends, but you can say the FD, which is really based on the imaging registration parameter, has a very marginal effect. But the largest effect is actually those DI, drowsiness index. And we also found because we use the mask to do the temporal scooping, we found a significant overlap between those DVAS masks and those DI masks. But if we exclude the overlap, use the device-specific mask, do the temporal scooping, we see no change on the resonance state connectivity at all. So it basically suggests that arousal modulation may mediate the relationship between the head motion and the resonance state connectivity. And for the FISO and the FMI correlation, I think it's similar. I think a few years ago, people used also do the EEG FMI experiments. They found the correlation between the FISO and the FMI, but largely depends on the alpha power, which is the indicator of the vigilance level, as well as the eyes closed, eyes open condition. Eyes closed condition, you see a significant correlation, but for the eyes open, more alert condition, those correlations are actually gone. A more recent paper from Jeff Dunn's group, they do also correlate the FISO data, which is like the pulse signal from the fingertip, and the resonance state FMI. They found a very strong correlation, not only in the gray matter region, they actually see the correlation in the white matter region as well, even though they have different dynamics. But from the data they gave to me, actually those pulse signals actually also highly correlated with the EEG low frequency band and the K complex. That's also an indication there's some like the arousal fluctuation during those light sleep stage. And also based on the finding, those white matter also shows the large changes. So there may be the second mechanism in addition to those neural activity through which the arousal modulation can affect the FMI signal, which is more like through the sympathetic system. And I will skip that one. Okay, so far then we have this figure, but this is just one demonstration. I want to say is the same thing could apply to the other things, because arousal is a very complicated factor. Some disease has very different arousal, and also it's going to affect the behavior as well. So these two things has been linked to the resonance state connectivity. So I think the critical aspect of my talk is whether some of those correlation is mediated by the arousal modulation. Yeah. If you just check literature, I think you can see a lot of results actually show those sensory dominant pattern. So I think if you see this pattern, you should be careful. And in some way, I think the dynamic connectivity comes from those instantaneous brain resonance state FMI co-activations. Those co-activations is indeed from the neuronal co-activation. And specifically, those global co-activation is induced by the transit arousal modulation, which is showing as the SST event in the electrophysiology signal. Those arousal events may mediate the correlation between resonance state FMI and those non-neuronal signals. And the sensory dominant pattern and the transit nature of those global caps will cause systematic and the dynamic FMI connectivity change. So it might be misinterpreted as meaningful connectivity change. So if you see something similar, those sensory dominant pattern in your results, I urge you to check the global signal first. Yeah, that's as my talk, and I just want to thank you, the person contributes to those results and also the funding agents. Yeah.